Hello, it's Stat135, lecture 34. Last time we were focusing on simple linear regression and computing the variance of beta 0 hat and beta 1 hat, and we got the following formulas, as well as the covariance of beta 0 hat and beta 1 hat. However, generally we don't know what sigma squared is, so we need an estimator for it. So that's the first thing we're going to do today. Once we have standard errors, we're going to then compute confidence intervals for the parameters. So we're going to define the residual sum of squares to be the sum of the residuals squared, and we're going to normalize our data so that the mean of our predictors is 0. And this amounts to translating our scatter diagram horizontally by x bar units so that the center of our data is now 0. This doesn't change sigma squared or RSS since the Tychian regression line move with the points. So what we're going to do is we're going to show that the sum of the residuals squared over sigma squared is a chi squared with n minus 2 degrees of freedom by first showing that the square of the errors over sigma squared is chi squared with n degrees of freedom. So we start off with the sum of the squares, and so the sum of the squares is, so the ith error term is yi minus beta 0 minus beta 1 xi. So essentially, our response minus the corresponding value on the Tyche line squared, and we're going to do some algebraic nonsense where we add and subtract the same term so that we can write our. So we have a different expression now where we have a, b, and c all squared. When we square them, we get a squared plus b squared plus c squared plus cross terms, and all the cross terms are 0 thanks to the following things. Our assumption that the average of our data is 0, and then our normal equations that we derived last time. The sum of the residuals is 0, the sum of the xi times the residual is 0. Those tell us that the cross terms are all 0. And so then the sum of our errors squared over sigma squared is a sum of 3 terms over sigma squared. And here I am assuming that x bar is 0. And I'll notice that so I'm going to notice some things here. Let's see here. So first of all, beta 0 hat, we do know that that has expectation beta 0 and variance sigma squared over n. And we do know that beta 1 hat has expectation beta 1 variance sigma squared over n variance x. So that just comes from the top 2 lines here, something we worked out before, and the fact that x bar is 0. So, but what about normality? Well, so since our standard statistical model is y is beta x plus e, with our xi's being constant and the ei's being independent normals, it follows that the yi's are independent normals. And furthermore, since beta hat is x prime x inverse xy, beta 0 hat and beta 1 hat are linear combinations of independent normals, in other words, the yi's, which is normal, right? A linear combination of independent normals is normal, and hence beta 0 hat and beta 1 hat are normal. Furthermore, any linear combination of beta 0 hat and beta 1 hat, such as like a beta 0 hat plus b beta 1 hat, is a linear linear combination of independent normals, y1 to yn, and hence is normal. It follows that beta 0 hat and beta 1 hat is bivariate normal, because if any linear combination of normals is normal, then those two normals are bivariate normal. And more is true since the covariance of beta 0 hat, beta 1 hat is 0 when x bar is 0. It follows that beta 0 hat and beta 1 hat are uncorrelated bivariate normals, which are independent, because uncorrelated is equivalent to independent when you have bivariate normals. So hence, the first two terms on the right-hand side of the equal sign are independent chi-squared 1 degree of freedom. Hence, their sum is chi-squared with 2 degrees of freedom. And furthermore, because the error terms, the EIs, are homoscedastic and hence independent of the XIs, the sum of the EI square over sigma squared is independent of the first two terms. So the chi-squared with n degrees of freedom is independent of the chi-squared with 2 degrees of freedom. Hence the residual sum of squares over sigma squared is a chi-squared with n minus 2 degrees of freedom. And we say that the residual sum of squares has n minus 2 degrees of freedom. So we know that the expectation of a chi-squared with n minus 2 degrees of freedom is n minus 2, and hence the expectation of RSS over sigma squared is n minus 2, and hence the expectation of RSS over n minus 2 is sigma squared. So we have an unbiased estimator of sigma squared, namely RSS over n minus 2. We'll call that s squared. And that is a great find. So now that we have our estimator for sigma squared, we can make confidence intervals for beta 0 and beta 1. So recall from chapter 6 what a t-distribution is. It's a ratio of a standard normal and a chi-squared with n degrees of freedom over n square rooted. And so I'm going to make my standard normal using beta 1 hat and my chi-squared using RSS over sigma squared. And then I get a t-distribution with n minus 2 degrees of freedom is square root of, so is beta 1 hat minus beta 1 over the standard error. And that standard error is square root of RSS over n times n minus 2 times the variance of x. So great to know the standard error of beta 1 hat. This will allow us to do hypothesis testing, to make confidence intervals, all sorts of good stuff like that. And so we can find a 95% CI for beta 1 hat plus or minus Tn minus 2.025 standard error, beta 1 hat. Awesome. And you can do the similar thing for beta 0 hat. So the variance of beta 0 hat is sigma squared 1 plus n plus x bar squared over n variance x. And so you can just in exactly the same way make the t-distribution, and Tn minus 2 is beta 0 hat minus beta 0 over the standard error, where the standard error is square root of RSS over n minus 2 times 1 over n plus x bar squared over n variance x. And so then we get a 95% CI, beta 0 hat plus or minus Tn minus 2.025 standard error. It's all great stuff. So I wish you all a happy long weekend, and I'll see you next week.